In this video, we will discuss activation functions, which are one of the most important components of any neural network. So, an artificial neural network, as we know, simply calculates the weighted sum of its input and then add a bias to it and then decides whether that neuron should be fired or not. Now this value of y can be anything ranging from -infinity to +infinity. A neuron really does not know what this bound of the value y should be. So if we look into this equation very carefully, we will realize that a neural network without an activation function is simply a linear regression model. Without activation function, our neural network will not be able to learn and model other complicated features other than linear models, other complicated features such as image, audio, or speech. So we need a neural network that can be modeled to learn and represent almost anything and any arbitrary complex function which can map an input to the output. So why do we need an activation function? So we need an activation function so as to make our neural network more powerful and to add ability to it to learn something very complex and complicated from the data, and also to represent any non-linear complex arbitrary function mapping between an input to the output. We need to decide whether a neuron should be fired or not, or should be triggered or not. So this is exactly how our brain works. So for our tongue to feel the taste, certain taste buds or certain neurons has to be triggered. So this is exactly how a neural network works. So for a neural network, we need to trigger or fire some neurons. And for this purpose, we add an activation function. So we need an activation function to check this value of y produced by a neuron and to decide whether outside connections should consider this neuron as fired or not, or say activated or not. So in short, the activation function, also called as transfer function, is used to determine the output of a neuron. It maps the resulting values which we get from the multiply add process to a value in between, say 0 to 1 or -1 to 1 range depending upon the type of activation functions that we use. There are two types of activation functions: the linear activation functions and the second type, non-linear activation functions. So the linear or the identity activation functions, as you can see from this figure, is a line or it is linear. Therefore, the output of this function will range between -infinity to infinity. Or in short, the output of this function is not confined between any range. So since for a linear activation function, the function is like a straight line, this linear activation function does not help with the complexity or the various parameters of the usual data that is fed into our neural network. That is why we have non-linear activation function. The non-linear activation functions are the most used activation functions in our neural network. And this non-linearity helps to make the graph as shown in this figure, right? So that means it makes it easy for the model to generalize and adapt with the variety of data and to differentiate between the output. Or in short, the data presented around us is very complex, and the relationship between the input and the output is not simple like just a straight line, but instead it is very complex. So in order to recognize this complex pattern where the output is influenced by many input, usually the relation tends to be non-linear, turning a simple line into something like a curve. And therefore, we use non-linear activation function for non-linear data that is presented to us. So we know most of the times the data used to train our neural network are unstructured data, and they are non-linear data. So in that case, it is important to use a non-linear activation function. And there are different types of non-linear activation functions which are mainly divided on the basis of the range or their curve. The first thing that comes to our mind when we think about activation function is, how about an activation function based on a threshold value? Or in other words, if the input to the activation function is greater than a threshold value, then that particular neuron is activated. Else, it is deactivated, that is, its output is not considered for the next hidden layer. And one such activation function based on threshold is what is called as the step function or the binary step function. So as we can see, its activation function f of x is equal to 1 if the value of x is greater than or equal to the threshold value, which in this case is 0, and the activation function is equal to 0, that is, that particular neuron is not activated if x is less than the threshold value, which is x is less than the threshold 0. So this is a very simplest activation function which can be implemented with a single if-else condition in Python. And for this function, if I gave the function call to be binary step 5, so 5 is greater than 0, so definitely the return value will be 1. So this is a mistake. It should not be 5. It should be a 1. And if I make a function call to binary step as -1, since -1 is less than 1, definitely the output will be 0. So again, remember, this is a mistake. This is not 5, but instead it is 1. Now, where do we use this step function as our activation function? For example, suppose you are creating a binary classifier, then a step function could be one of your choice because it exactly does what you are trying to do. That is, it will give you an output as either 0 or 1, class 0 or class 1, or yes or no. But think about another scenario wherein which you would want multiple such neurons to be connected to bring in more classes like class 1, class 2, class 3, etc. Or in short, you are trying to build a multi-class classification problem. Now, in that case, if we use a step function, what will happen? So consider a case wherein which you used step function in a multi-class classification problem and more than one neuron gets activated. So all neurons will suppose that all neurons get activated, which means that it will give a result of 1. In that case, how will you decide whether the output belongs to which class or not, because all the neurons are now activated? So in that case, you would want the neuron to activate, or you want your network to activate only one neuron and other neurons should be 0. But if you are using a step function, this is a hard to train and converge in that manner. So will it not be better if you had an activation function that was not binary, but it would instead say 50% activated or 20% activated and so on? And then if more than one neurons get activated, then you can find which neuron has the highest activation function and go with that particular neuron to be fired. And this is exactly what happens in a softmax activation function. So softmax is something which I will cover in the later slides, but softmax is just an advanced version of having a step function. So one definite drawback of a step function is that it cannot be used in a multi-class classification problem. But there is also another drawback of step function. That is, the gradient of the step function is always 0, which causes a hindrance in the back propagation process. So if we calculate the derivative of f of x with respect to x, that is nothing but our gradient, we will get that to be equal to 0 for all x. Because remember, from our previous slide, the activation f of x is equal to 1 if x is greater than or equal to 0, or it is 0, right? So in this case, f of x is a constant value, either 1 or 0, and the derivative of a constant value is nothing but 0. So whatever our x value be, the gradient or the derivative of my step function will be always 0. So we also know that the gradient is important because they are calculated in order to update our weight and bias during our backward propagation. So in this case, since the gradient of the function is 0, the weight and the bias does not get updated. So this is again another drawback of step function and why we don't commonly use that in order to train our neural network. The next activation function we will discuss is sigmoid function. So as you can see, sigmoid is a smooth function from this figure. And the sigmoid function is in the range 0 to 1. As we can notice from this figure, between the x values, so this is my x-axis and this is my y-axis. So between the x values -2 to +2, the y value changes very steeply, which means any small change in the value of x in this particular region will cause the value of y to change very significantly. This means this function has a tendency to bring the y values to either end of the curve. So sigmoid activation function looks like it is a good fit for a classification problem, as it tends to bring the activation to either side of the curve, making clear distinction on the prediction. A sigmoid activation function is represented as A is equal to 1 by 1 plus e raised to minus x. And this can be represented as a Python pseudocode as like this. to this sigmoid function, when we apply the function called sigmoid function 7 and sigmoid function minus 22, we get the output as below. So as we can see, the first output is 0.99 is closer to 1, whereas the second output 2.7 into 10 raised to minus 10 is close to 0. So that means the first output can be approximated to the binary classification for the class 1, and the second output could be approximated to 0 to the binary classification for class 0. But sigmoid activation function also has its own problems. For example, if we look towards the end of the sigmoid function, that is at this point and at this point of the graph, the y value tends to respond very less to the change in the x value. So in this graph, this does not stop here, but it continues like this. Similarly, at this end, it continues like this. So as we can see, to the end of this graph, the sigmoid function, the y value tend to respond very less to the change in value of x. This means that the gradient at this particular region is going to be very small. And this gives rise to a problem called as vanishing gradient descent. So what happens when the architecture reaches the near horizontal part of the curve on either side, that is this position and at this position? So in that case, as you can see in this figure, the gradient becomes small or has vanished. So the gradient is, or gradient which is otherwise called as the derivative, is what is shown in red color. So as you can see, the gradient is only significant at till this position, and after that it is almost the same, or it is very small or has almost vanished. And so the network refuses to learn further, or it becomes dramatically very small. So sigmoid activation function squashes a very large input space into a small space between 0 and 1. Therefore, a large change in the input of the sigmoid function will cause only a small change in the output. Or in short, the derivative or the gradient becomes small. Now for small neural network with only few hidden layers, the use of this sigmoid activation function will not create any big problems. However, when the number of hidden layers increases, it can cause the gradient to be very small for the training to work effectively. As we know, the gradient of a neural network are found using back propagation. Or simply put, the back propagation finds the derivative of a network by moving layer by layer from the final output layer to the initial ones. And by the chain rule, the derivatives of each layer are multiplied down the network to compute the derivative of the initial layers. However, when we have, say, n hidden layers and we use a activation function like sigmoid, then it creates n small derivatives which are multiplied together. Thus, the gradient decreases exponentially as we propagate down to the initial layers. A small gradient means that the weight and bias of the initial layers will not be updated effectively during the training session. Since these initial layers are often very crucial to recognizing the core element of the input data, this whole situation can lead to an overall inaccurate network. Now, of course, there are solutions to overcome vanishing gradient descent problem. The simplest solution is to use other activation functions like ReLU, which again we will discuss in our coming slides. Other two solutions for vanishing gradient descent problem is one called as residual network, which again we will learn in our course, and the second method to solve it is what is called as batch normalization. So the three solutions for vanishing gradient descent problems is the first one, to use a different activation function like ReLU. Second one, to build a residual network. And third one, which is called as batch normalization. Batch normalization. So as I have mentioned, batch normalization is one technique to overcome the drawback of using a sigmoid activation function, which is the problem of vanishing gradient descent. So let us see how batch normalization resolves this issue of vanishing gradient descent. So as I have stated before, the problem of the sigmoid activation function arises because a large input space is mapped to a small range, that is between 0 and 1, causing the derivation, or what we call as gradient, to disappear. So batch normalization reduces this problem by simply normalizing the input so that the mode I'm considering mode because mode means positive as well as negative value of x. So, but how it does is the batch normalization reduces the problem of vanishing gradient descent by simply normalizing the input so that mode x does not reach these outer edges of the sigmoid function. So the outer edges is these and these. So it makes sure that the batch normalization makes sure that the value of x does not reach those outer edges of the sigmoid function. So as you can see in this figure, it normalizes the input x so that most of the x values falls in this green region. So most of the x values after batch normalization will fall in this green region where the derivative is not small. So derivative is shown by this red line, red broken line. So what we do is we normalize all our x value into this green region, and in the green region we can see that the derivative is not as small when compared to these near horizontal lines of the sigmoid graph at these positions. So this is how batch normalization overcomes the problem of vanishing gradient descent. The next activation function we will discuss is softmax. We already know that the sigmoid activation function returns values between 0 and 1, which of course can be treated as the probabilities of a data point belonging to a particular class. And thus, the sigmoid activation functions are widely used for the binary classification problem. The softmax function, which I have already mentioned in the previous slide, is used for multi-class classification problem. This function returns the probability for a data point belonging to an individual class, and the mathematical expression for the same is as shown in the slide. Now, while building a neural network for a multi-class problem, the output layer would have as many neurons as the number of classes in the target. For instance, if you have 3 classes, there would be 3 neurons in the output layer. So a softmax can be written as a Python code as shown in the slide. And suppose that you have got the output for the neuron as 0.8, 1.2 and 3.1. Now applying softmax over these three values will give you the following results, that is 0.08, 0.1 and 0.8. So these represents the probability for this data point, for this particular data point to belong to each of the three classes. So this represents the first class, second class and third class. Also, one thing to note is that the sum of these values, that is 0.08, 0.1, 0.8, will be equal to 1. The next activation function we will discuss is tanh. So the figure shows a tanh function, and as we can see, the range of tanh is from -1 to +1. So this is my y-axis and it ranges from +1 to -1. Mathematically, the tanh function looks very similar to a sigmoid function. Tan h is equal to 2 by 1 plus e raised to minus 2x minus 1. And this could be rewritten as 2 into 1 by 1 plus e raised to minus 2x is nothing but sigmoid of 2x minus 1. Tan h function, as we could see from this figure, is symmetric around the origin. Or to give a more clear example, you could look into this figure. So it is symmetric around the origin, unlike the sigmoid activation function. Talking about the gradient or the derivative of a tan h function, in figure 1 you have the gradient of the sigmoid function, and in figure 2 you have the gradient of the tan h function. As we can see, the gradient of the tan h function is steeper as compared to the sigmoid function. So like the sigmoid function, the tan h function also suffers from the problem of vanishing gradient descent. However, this vanishing gradient descent in tan h is not as significant as that of the sigmoid function, or it is not as problematic as the sigmoid function, because in the case of tan h the slope becomes a bit more steeper when compared to the sigmoid. Tan h is also a very popular and widely used activation function. Now you might be wondering, how will we decide which activation function to choose? Usually, tan h is preferred over sigmoid activation function, since, as I have shown in the last slide, the tan h is zero-centered, and also as we see from this slide, the vanishing gradient descent is not as problematic in tan h when compared to sigmoid function. And because of these two reasons, whenever you have to choose between a sigmoid or a tan h function, we probably go with the tan h function. The next popular activation function we will discuss is ReLU, which stands for rectified linear unit. So ReLU is another nonlinear activation function that has gained popularity in the deep learning domain. So as we can see, the rectified linear unit or the ReLU function is f of x is equal to max of 0, x. That is, if x is less than 0, f of x is equal to 0. So if x is a negative value as shown in this figure, f of x is 0. And if x is greater than or equal to 0, f of x, that is ReLU, is equal to x. So that is what is shown here. And as we can see, the range of ReLU is from 0 to infinity. As we have already discussed, ReLU activation function is a solution to overcome the problem of vanishing gradient descent. ReLU has also got another advantage. That is, the ReLU does not activate all the neurons at the same time, which is it has control of the sparsity of the activation. Imagine a big neural network with a lot of neurons. Now, if you use a sigmoid or tanh function, so sigmoid function has a range between 0 to +1, and tanh has a range between -1 to +1. So when we use a sigmoid or a tanh function, it will cause almost all neurons to fire in an analogous way, which means all the activations will be processed to describe the output of a network. In other words, the activation becomes very dense. And this in turn is very costly. So we will want ideally only few neurons in the network to be activated, whereas few other neurons to remain inactive, thereby making the activation sparse and efficient. It was recently proved that ReLU had 6-time improvement in convergence when compared with tanh activation function. But of course, ReLU has its own shares of drawback. For example, if we look at the left side of this graph, you will notice that the gradient value is 0. So to be more clear, let us go and see what the gradient of a ReLU function will be. So the gradient of or derivative of ReLU is f dash of x is equal to 1 if x is greater than or equal to 0, and it becomes equal to 0 if x is less than 0. So there are cases when the gradient vanishes to 0. Due to this reason, during the backpropagation process, the weight and bias of some neurons are not updated. And this can create dead neurons, which never gets activated. And this problem is what is called as dying Rayleigh problem. And this dying Rayleigh problem can cause several neurons to just die and not respond, making a substantial part of the neural network passive. However, there are variations that could be made in order to mitigate this issue by simply making the horizontal line into a non-horizontal component. And this variation of Rayleigh is what is called as leaky Rayleigh. For example, this figure on the left shows Rayleigh and the figure on the right shows leaky Rayleigh. And here you can see this horizontal line, which is actually causing the dying Rayleigh problem, has been given a slight slope in the leaky Rayleigh in order to overcome the problem of dying Rayleigh. So here y is equal to, the f of y is equal to a into y for x less than 0. So rather than just a horizontal line, we have an inclined line when x is less than 0. So the range of leaky Rayleigh can be from minus infinity to plus infinity. So when we consider the gradient of a leaky Rayleigh, we have f dash of x, that is the gradient or derivative of leaky Rayleigh, to be equal to 1 if x is greater than or equal to 0 and is equal to 0.01 if x is less than 0. Now, one more thing to keep in mind is that Rayleigh should only be used within the hidden layers of a neural network. So for the output layers, we should use a softmax function or a sigmoid activation function depending upon the type of classification. Choosing the right activation function. Now that we have seen so many activation functions, we need some heuristics over how to choose these activation functions and under which situations we need to use them. So some of the heuristics that you can have in mind is, first, sigmoid functions and their combinations generally work better in the case of classifiers. The second rule of thumb is sigmoid and tanh functions are sometimes avoided due to vanishing gradient descent problem. Third, Rayleigh function is a general activation function and is used in most cases these days. Next, if we encounter a case of dead neuron in our network, the leaky Rayleigh function is the best choice. Next, always keep in mind that ReLU function should only be used in the hidden layers. As a rule of thumb, you can begin with using ReLU function and then move over to other activation functions in case ReLU does not provide with optimum results.